All right, we'll go ahead and get started. So first of all, just good afternoon and welcome to the CMU SubT finals recap and a look at what's next. My name is Chris Kissel. I'm an Associate Director of Corporate Partnerships in the School of Computer Science, and I'm here at Carnegie Mellon University. And thank you so much for joining the event. Also, just a few housekeeping items before we begin. Please note this event is on the record, it's being recorded. And if you'd like to post a question, there is a button at the bottom of your Zoom window. It says Q&A, and go ahead and post your question there. And at any point, we would love to see it. We'll take a look at it, prioritize it, of course, and would love to then consider that for answering. So even right now, if you have any question at all, the team would love to hear from you. So please feel free to use that. Also today, I am joined by the SubT Team Explorer leadership, Sebastian Scherer, Associate Research Professor, and Matt Travers, System Scientist. And both are in the Robotics Institute in the School of Computer Science. So at this time, I'd like to, again, welcome you to the conversation. And I'd like to turn things over to Sebastian and Matt for giving us a little recap of what happened these past 3 years and to take a look at what's coming up next. Thank you.
Thanks, Chris, for the introduction. And then I'll just briefly share my screen. So I think the idea, a lot of you have seen already over the years what we've been up to, and we'll just do a kind of very quick recap, and then dive a little deeper into what happened in the final circuit. I think is something that a lot of people are interested in, and then we really want to keep it interactive and take a lot of questions. So please think about what are you really interested in, and we don't want to kind of go through 100 slides and really do that. So just to recap, the challenge is to rapidly gain situational awareness of underground terrain, and there's a lot of challenges you would have to overcome. And the goal is to find and classify and localize as many artifacts within 60 minutes as possible. So just a very quick recap. Our team had about 90 total active members over the last 3 years. And thanks to a lot of our sponsors for supporting us. We had here just a couple of pictures from the various challenges. On a very, very high level, our team had these kind of ideas of modular autonomy and trying to have resilient autonomy, and that's what we tried to push in the challenge. For the final circuit, we showed up with 3 ground robots, so two of the larger ones and one smaller one, one walking robot, which you see on the left here, and then 4 smaller drones and 3 larger drones. And over the last 3 years, we've developed a lot of very exciting algorithms, and then also brought them together in a kind of coherent system. And so we'll not talk. I will not go through a lot of the details there. There will be the seminar on November 19th. The RI seminar is open to anybody. There's a Zoom link for that seminar as well. And if you're in Pittsburgh, you're welcome to attend in person. We can go through some of these as there are questions. I think for now, the idea was maybe we'll just go straight to what to the analysis from the events. Go through that a little bit, and then we'll open up to questions. Maybe in those we'll get to some of the technical details. So just to kind of recap, for the tunnel circuit, we had more than double the points and got first. In the urban, we placed second, and then in the final competition, we placed fourth and also explored most sectors. And so I'm sure you guys are excited, why did all the other teams get better, or did we get worse, or what happened? And I think a lot of it comes down to is these challenges have a lot of variables, and we'll see kind of what happened. So for the final competition, what we ended up going with is 3 ground robots, the walking robot, and we sent, let's see, 3 smaller drones and 1 larger drone was our team of robots. And so here next you'll see a replay of the competition, the 60 minutes in 3 minutes. And the upper right tells you the period, so between 0 and 10 minutes, and some highlights. So we start out with sending R2 towards the tunnel portion of the circuit. Then R1 goes towards the urban portion of the circuit, and R3 goes towards the cave section, which is much narrower. Once they're out exploring, then now the ground robot that's in the urban circuit launches the drone, which is the yellow arrow. And now that drone DS4 is off exploring. Here the drone gets stuck in fog a bit, and then explores some more, and then tries to get into the cave area, and then returns home. The ground robots in the tunnel is currently somewhat stuck in the tunnel because there's also fog in the tunnel. And R3 is out exploring the cave circuit, which is the purple. In blue is R1. It's in the currently what's called a warehouse room, and is exploring that area. So at this point, we've actually seen a large part of the course, and actually the part that probably most other teams have seen up until in the entire competition. Now here, R3 actually explores very deep and gets closer. And so here, some of the later that will become clear. Some of the objects we've lost. We have out of comms with the blue, which is R1, and R3 at this point. So we're sending in another drone here to receive some data from R1. So you can see it goes towards the cave, and then explores a little more and comes back. R3 now climbs up a hill here, and then there's a very treacherous ledge where it thinks it can go down, but then can't get back up. R1 is stuck at this point, and at this point we have completely explored the whole map. So this is actually within less than 30 minutes we had seen everything. And so right now only R2, which finally got unstuck from the fog, starts exploring some more. And then now at this point, there are several artifacts. We see that we are missing a lot of data from R3. So we send another drone down to try and rescue some data from from R3, the ground robot that fell off the cliff. We didn't know it had fallen off the cliff at this point. And so after that, the drone just goes out, explores some more, and comes back. So by this time, our operator is mainly focused on trying to submit artifacts and go through the list of artifacts. So now the return home time for the ground robot is set up, which was set to come back at 50 minutes. And so it comes back to the start gate. And sits there. So this was kind of our whole run in kind of a couple of minutes. Here you can see the map. So all of the robots calibrate themselves to the stars, and this is the map that the ground robots built over the run and the distance they traversed. Here you can see the drone maps of the 3 flights. Each of the robots kind of experienced some challenges. So R1 got kind of wedged inside a cave. The artifacts were collected by the drones. R2 had some issues in the fog, not because of regular traversability, but our robots have tried to avoid falling down cliffs, which is 515 is a sensor that had problems. R3 had fell off the cliff, and then PS1 rescued the data. And let's see what else. Yeah, so each robot kind of experienced some challenges. Here are some of the artifacts that we did not submit. So we got 17 points, 18 points was 3rd place. So we actually, in our base station, had an artifact that we did not, our operator kind of missed and did not submit. And then we had one gas artifact that our operator could have submitted for 19 points, but we never submitted. And then, so you can see a couple more views of this. And so just kind of the, how well could we have done if everything had gone well in this run? So if we had submitted all gas, cell phone, and artifacts, we would have been submitted 18, tied for 3rd place. And then if our operator had spent some time, had the time to adjust gas and cell phone artifacts, we would have potentially gotten 24. And if you had gotten artifacts from R3 without kind of adjusting any positions, we would have had 24 points. And then if you had time to refine and so on, our absolute highest score would have been 29 points. There are many lessons learned, and maybe we can go through some of these in the Q&A. I don't want to kind of go through too many details, but just kind of where are we going from here? I think on the high level, one of the things we learned is that even though the drones were already as small as we could make them, they're still about 50% too large and heavy. And so we really need to kind of switch the paradigms to a visual system. The other thing was that semantic exploration really needs a semantic context to decide between covering an area and prioritizing potential future areas such that would go through windows or openings. The other thing is object detection. And the challenge was kind of artificially constrained to only known objects, and so for actual deployments, you need to be able to quickly learn relevant classes and adapt on the fly. And so you basically need to be able to do this few-shot object detection in real time for a real mission. And the other part of it is that right now the ground robots are a bit too, made large to work well in kind of tunnel-like environments. But for realistic missions, they're a bit too large, and so we're working on making them smaller, having them better interact with our operators, and also have more capabilities such as platooning or beam deliberate comms relays. And so we have plenty of slides and things that we can go through, but we really wanted to keep this interactive. So the idea is that I'll stop here and then come come with your questions. So, while you, maybe Matt, do you want to take the first question here?
So where have some of the students moved on to from SubT?
Yes.
Sure. Yeah, so a lot of the students actually throughout the program have graduated and sort of gone their various ways. A lot of people took jobs in the industry sort of from that first team in the first year. We lost actually like majority of the people who, yeah, I think most of them kind of went either with the sort of medium-sized robotics firms. I think a couple went to like larger companies, Facebook. A fair number of people actually went to go do startups that have graduated. And we're probably like, I don't know, maybe 50-50 graduated, 50% are still here at this point. We had a pretty large, just like combination of students, probably undergrads involved, the majority graduate students, and then staff. So we've retained, people that were here, they actually work here. It's worth mentioning also that at least for us, these projects are going, the SubT and a lot of that work is continuing on with work that we've been doing now for a couple of years with USASOC. And again, starting to take some of the technologies, core component technologies, a lot of the SLAM, a lot of the coordination behaviors, and then the nuts and bolts of that. So a lot of students are actually continuing to work on this sort of like line of research. And then there's also the DARPA Racer program, which is another follow-on program where like, roughly the same sort of set of people and the same, sort of system of working people in and getting them up to speed on this like particular set of capabilities, like autonomous capabilities, is another thing, at least for us internally, where a lot of the students are starting to point their attention as well now.
Thanks, Matt. So I think there was, the other thing I just wanted to mention is are there any particular technologies that you want us to talk about? We have plenty of things to talk about. If you want any kind of deep dive on anything in particular, just post a question and let us know. So maybe I can read the next question, and then Matt, you want to answer, and then we can kind of go back and forth. So what's the future of the robots? Will they be repurposed?
So yes, short answer. On the drone side, maybe Sebastian can fill in a little bit about what that sort of pipeline looks like. R1 and R2. So the short answer is we want to probably turn something like after R3, which is the robot, the smaller of the 3 ground robots. So once that took a dive off the cliff, we'll probably want to redesign Asper, just put that basically back together. That system did particularly well in the cave, and like further evaluating its mobility and just getting that ironed out for like future search and rescue deployments is exactly what we're thinking on that vehicle. So that would be like a 1-to-1. And then on the spot and on some of the payloads, we're exactly reusing them right now in other projects, and sort of trying to mature that the technology that was on them and start to just really actually go see, for different deployments, not just the DARPA sort of, parameterized subterranean challenge, going out and really seeing what we can do as we deploy these robots.
Yeah, and then just briefly on the drone side, yeah, we are still using the drones for similar purposes. It was kind of underground exploration, So I think then the next question is, are you looking for volunteers? Well, the challenge is done, but we're definitely looking for, always looking for people for all the other things that are happening. Some of the continuation projects, like Matt mentioned, there's DARPA race, there's some projects on this kind of exploration, and lots of projects happening. So definitely let us know.
Are there other areas of DoD that you're working to transition tech to? Ashley, you want to field that?
Yes. So I think there's definitely some of the components are kind of spreading throughout various programs. Just an example, like an easy one is always the SLAM system, because it's very general. Every robot wants SLAM. So that's, for example, on DARPA Racer is being used. We're using it in some of our projects. And then, and I think then the other one that Matt mentioned is more direct, is essentially uses or has some very similar missions where they want to go underground, that we work with them.
So is there any adoption of CMU research from RI that was implemented during development? Yeah, so yes, there are two specific things in terms of like research adoption. Is we did 2 best paper awards. So the aerial drone coverage was actually out of Oregon State, and then the ground robot exploration strategy were both won actual best paper awards at different conferences. So short answer, yes. We've had then multiple master's students whose master's theses, certainly on the the aerial actually planning side, the comms planning side. So yeah, probably the most like quantified way to see this is to look at like master's thesis and sort of the really high quality thereof for those, and then as well as then the more black and white would be in terms of the conference papers and the conference papers that have won awards in particular.
Yeah, I think this is good. And then, so can you briefly go through the SLAM pipeline? So yeah, I can show a little bit. Share my screen again. Can you see the screen?
Yes.
Okay, cool. So the SLAM pipeline is actually something we developed in the challenge, and it's based on, we call it super odometry, and the idea is essentially the IMU, everything's anchored to the IMU, and then various external sensors correct drifts in the SLAM system. And then additionally, there's also a loop closure algorithm that runs in to address any drift. We actually did develop a multi-robot loop closure algorithm that would fuse these things together, but we found that that it's a bit fragile to do this multi-robot SLAM, and so we are just doing single robot loop closure. And then so you can see a little bit. We can play this a little bit, so you can see. We take the point cloud, extract the features, and then based on those features, we adjust the SLAM. And so we spend a lot of effort actually making that system robust. These SLAM algorithms often have various magic parameters in terms of how many features to extract, how to match these together. And so we wanted this to, for example, work here in narrow to wide space, and you can see it here in a corridor. It has different criteria, and to then when we go to bigger areas, it will adjust some of its the voxel size depth, for example. Additionally, it's also aware of how much computation you have, so it will choose different features depending on, we tune it for the kind of available computation. And some other things we had to handle are dust that can often cause some instabilities. We explicitly detect dust and reject it. So this is enough detail for this SLAM. Then can this technology be extended to space exploration as well, like mapping Martian caves and lava tubes? And the short answer is definitely. I think that would be definitely something that's feasible.
All right. From a high level point of view, what from Eric Crackpot? Hey, Eric. The most, all right, so what did the challenge most advanced relative to the SOA? Guessing, not mobility or manipulation. Was it about coordinating the multiple threads of exploration or fusing everything into common operational picture? Yeah, I mean, I'd say that, yeah, like the practical, I mean, there's sort of both. There'd be like the practical state of the art where, right, like the capabilities, if you take like your average research paper on multi-agent coordination and compare it, I mean, still we, one had a couple best paper awards, but like what exactly is the current state of the art there? It'd probably be a little bit difficult to tell depending on who you ask, but one of the things I would definitely easily say was really on the integration side of things and getting everything into just one place, like for an actual system where it's hardware, it's software, it's this many different types of platforms going out, it's sharing the maps. And it's one thing to say that you're going to do multi-robot SLAM, and it's a whole nother thing to go out and actually like make it work in a cave where it's wet and sensors don't work and this driver doesn't. So just like getting all of that together, figuring out how to deploy like code onto the robots, right? I mean, once we had 12 robots, maintaining just the different pushes and different people working on different exploration strategies because you had different cameras, and just like getting all of that to a place where we now have like an actual, it's usable, right? I mean, we came in fourth place, don't get me wrong, but like it is a usable system. And it's remarkably, so that by far, long story short, the most remarkable thing I think in my perspective was like where we started in terms of actually being able to deploy multiple systems simultaneously to where we ended up, at least for our team, was like one of the largest deltas. I think figuring out the comms, to be honest with you, and really forcing us to think about what we were going to send and where, and even arguably that might have been one of our largest problems in the final competition, was exactly that. But just having to really get down for us, and not just, we can't just assume that everything is going to be perfect, right? And that really shaped throughout the competition, like whether you had comms, whether you didn't have comms, and how you interacted with your autonomy relative to those practicalities. I would say it was sort of, as robotics is right, I can do kinematics, I can figure that stuff out, but it was a sort of new way to think, to really start to remove some of the assumptions that you'd see in a more academic perspective, but just getting that, the systems engineering, I would say, was sort of one of the largest advances, at least from my perspective.
I think the other one is, I mean, there's a lot of specific innovations that also happen, and then in the end, everything has to come together as a system. And I mean, just like a couple, maybe I can show a couple of quick examples just to, kind of motivate us a little bit. I mean, just for example, something that you wouldn't normally do is to try to make a system resilient to really handle dust or to be able to do emergency landing for drones, right? Like that's something you would never do. And so you'd end up, for example, here we're flying into fog that DARPA had put out. Eventually it works okay. At some point it's too much and the system realizes it, essentially does kind of rewind and then comes back, right? And like here it actually gets stuck on something for a while, then gets itself out. And so having this resilience in a system is really important to be able to have robust exploration. It's not only about like where do you send it and is your slime good. There's a lot of these behaviors that need to happen. Like for example, here is the drone's last good landing spot is this red ball here, and then now it has found a new spot, and then basically here it says, oh, I can't come back in time, and then comes home and lands. And so these kinds of things, similar on the ground robots. Let's see, where did I put it? Is like a same issue. Where did it go? So these are just some examples, but we had the same thing for ground robots. Is kind of recovery, where at some point when you get stuck, you kind of back off again, and all of these things, I think, in the end have to come together, and this behavior of the system overall was something where I think things worked okay, but it was something a little bit more that we learned over time is, you really build up this big behavior tree is what we used to say, hey, now the robot should do this, and if this happens, then now you can transition to this behavior, and to really have always some autonomy in the system. I guess the next question is, how long would it have taken a crew of, say, 3 people to explore the terrain? So I think this question, is a little bit, if you're just walking there, kind of strolling around in that final competition course, you can probably explore that in 15, 20 minutes with 3 people. But I think part of what we learned kind of in the competition is that, for example, if you're going into a tunnel rescue situation where you have to go in, your progress is going to be very slow because you have to be sure, okay, is this safe, breathable atmosphere? Can I progress further? And so on. I think that you agree with 20 minutes, Matt?
Yeah, I'd say that. I mean, it's, yeah. Just going out and actually,
I mean, maybe a little longer. I mean, it's maybe half an hour. I mean, to get really into all the rooms and make sure everything's covered. Yeah.
I mean, you start to face, one of the things that does, I mean, right, human mobility and their semantic understanding is going to obviously be far, well, not obviously, but my guess is, educated guess is that they'd be far, far superior to what we were working with. But in these underground environments, and like one of the reasons we have follow-on projects, even with like the ESASOC folks and whatever, is like it's still a huge problem is like coordination and localization, even for humans, when you start to have teams of people, are not necessarily solved problems, right? So like being able to primarily now, right, in operational scenarios or like search and rescue, whatever, right, like people typically just go down tunnel, and then it's a commander sitting, at the mouth of the tunnel, similar to our base station, and they know roughly where people went. But certainly I would not say that the norm is like actually knowing how to localize or knowing in real time where anything is. So like, those are going to be, again, obvious portions of the search and rescue or whatever task for humans, because you have the degraded comms, because you don't have situational awareness necessarily all the time, because you don't necessarily have great localization. It's not as like black and white as to why, the robots might actually do surprisingly good in comparison to what you would think they would relative to the humans, just because like even for people, it's not an easy problem.
Yeah. Okay, so one question is, what's the what detail is most important to make it work? From Yoyu, and I think the answer is there's a lot of details. like basically any detail is important. So if one of them doesn't work, then I think our robots don't work. And which research topic do you think is the most important and needs more work? I think from my side, and maybe Matt has also an answer, but I think from what I realized over time is, it's similar to a lot of systems, is where, at some point we start, you have an algorithm, it has some parameters, and then, at some point we test in many different environments. At some point you end up tweaking those parameters, and then you can't generalize anymore. And so getting and that's definitely something where learning can come in, and it's just hard in these challenges to make that work in time, I think.
I don't know if it's a research, well, maybe, I mean, again, I think it's bounding, like, right, I mean, there's this great unknown, because you need a system that's complicated enough that it can actually address the challenges, but like you need to find a balance where it's like not so complicated where you're trying to solve every problem that like you just run out of time, right? So like that, I would just say, and many of the teams sort of had, we're just in talking to them sort of informally, I think that was sort of it's a really difficult thing to know in these challenges, right? Because you don't know what the final course is going to look like, and it becomes obvious once you're there what the correct decisions are. But trying to plan for that, I would say, was like an especially challenging thing. Where like, we have the experience now from doing it, but like how you could like quantify that and use it as a teachable moment for like other people, I would say like. Right, like that's still a very, very big open question of how you strike that balance.
Yeah, so I think one thing I'll do is I'll play a video kind of just in the background for you to look at, just because I realized we just showed this abstract thing and you never even saw a robot move. so we'll show like the ground and then the air robot. And then in the meantime, I think we can answer some questions. So, where did we deploy most personnel? From Yoyu, I think it was pretty evenly split between ground and air, I would say. Like we have basically there's like each topic, like SLAM, object detection, ground autonomy, air autonomy, and comms, I think, was relatively even. I would say maybe 3 people each, something like this. Yeah, is that correct?
Yeah, I'd say it's roughly even.
And then, okay, how much deep learning was used? So we used here we use deep learning only for visual object detection. Okay, how similar to the competition environment is competition to our test environment? So it was a bit different, but I mean, we didn't, we tested, we tried to not overfit. We kind of learned our lesson in the urban circuit where we kind of overfit to the hospital, and then things didn't work when things were wider open. So here, we tested, and you can see this in the video. We tested in the caverns, Laurel caverns, which is pretty narrow, very similar to actually competition. Then Brady's Bend, which is an old limestone mine, which is on the outside very similar to, which is actually very similar to the actual cavern where the competition was. And then Hawkins, the hospital urban area where we're doing a lot of testing, which you can see here, was also very similar. So I think it was overall, it was somewhat similar. But it was definitely narrower than a lot of the places, I think, it was definitely on the narrow end of the things that we had seen before.
So is there any scope for research? There's a couple different comments here. So is there any scope for research in systems integration, or is it mostly just engineering? I mean, it's a good question. Yeah, like what's the science of being able to do systems integration? So I think there is, certainly. So, from our perspective, I mean, there's no, it seems, or at least it felt to me, sort of like you're following an ad hoc set of tools. And it almost feels like, every time you go to put together one of these more complicated systems, it almost feels like you need to come up with your new playbook or a new playbook. And I just, it would be hard for me to believe that there aren't things that you can carry over from one task to another. And right now, I think it's, sort of almost inherently like, it's more like tribal knowledge than it is a real science, right? Like things are passed on from one group to the next and from one experience to the next. But just because that has been my experience doesn't necessarily mean that there's not a more, analytic way to actually approach this, and a good way to, and I mean, certainly people are teaching systems level engineering or doing, operations research or something close to that, would probably have a better definition. But like in a specific, like the science of doing integration for autonomy on autonomous robotic systems, like I think that there's a ton of just science to be done and things to be explored and to really quantified in that general direction. But that's just my opinion.
Yeah, and I think, I mean, there is also, for example, on systems like the drones, I mean, it is a real problem. There's lots of trade-offs in terms of size, weight, power, and capability in terms of the overall system, right? Like how heavy do you make it? How much, how big is it? And so it's a real trade-off, and there's definitely something to do here. And I mean, a lot of it right now is kind of somewhat ad hoc in terms of how how we make these design choices, because there's an actual system. It's a system optimization problem.
Yeah, there's never been. It's been a 20 plus year. I'm a relatively young kid on the block, so to speak, when it comes to it. But like for my entire career, I mean, there's been a conversation about how what's the correct way to spec out a motor and a motor controller together. And I've never seen a robot where it wasn't a brand new conversation on every single time you did it. It's like you're starting over, and I mean, it's yes. I would say that in terms of like the delta, I would say that there's a ton, like arguably like some of the most research needs to be done in that direction. Like, SLAM and exploration strategies. I mean, you can tweak, you can do things better, but the technical readiness levels on those component technologies is actually pretty high, which is what you're like basically seeing in this competition. But again, like the biggest question marks didn't have to do with the SLAM or how to like put the SLAM together with the planning. It was more like scoping it on a more global level, where I would say it was more taking shots in the dark.
Yeah, and I think part of it we saw also in the performance, in the challenge. We can see the sensitivity of the system to the specific parameters of the challenge. Right, so we had practiced like some of the difference between our environment and the final competition was the final competition was much smaller in terms of size than the areas we had explored, and so it's just something. Some of these systems are exploration in particular is kind of sensitive to.
Yeah, so like we had never really had full comms until the final competition. Like everywhere else we had explored, we had just assumed that we were going to lose comms. So like in urban, let's say our biggest, well, other than we didn't prepare for stairs well enough, like our biggest issue for urban was that we relied on too much on there being comms. And in the final competition, arguably our largest problems with getting artifacts back was that the comms were too good and we had too much information going over the system. So just like, trying to come up with a plan that helps you mitigate both of those scenarios is more complicated than I would have thought.
Yeah, so one question is here, did you develop your own ground station interface? If so, do you have any lessons learned around what should not be included in this? Yes, so everything was built from scratch in the base station. And, of course, we actually had some human interaction, what is it called? Human HCII students work on a project to try and improve that interface. And so I think it was the interface itself, of course, wasn't very beautiful. It was not our focus, but I mean, I think it was effective. One of the user interface things that was missing, kind of in hindsight, that would have been a good idea is to have some sorting by confidence in terms of an object. Yeah, that's just something. And so there are a couple of things in that usability that we probably should have done a little better. Overall, I think it worked fine. And part of what we did in terms of the interactions, so for example, Matt mentioned the comms planning. Initially comms, like deciding when to drop comms nodes from the robots was a big workload for the operator, and so we ended up automating that, for example, to give more time to do higher level decisions and focus on the artifacts. So I guess last thing here is for the DARPA robotics trial, we gave an hour for the robots to complete all tasks. I did the task in 3 minutes without running. The human was easily 20 times faster than the best robots. So I guess the good thing is we're only 2 times slower now. So only a factor of 2 off. Yeah. Any other questions? Any other things you want to see?
I two sort of last plugs, I guess, if there's no other questions. So yeah, I didn't mention, so there is sort of a continuation of the underground map. So like the work that we're doing with USASOC and then the work that we're doing with the DARPA Racer program are very, very related to this program in the sense that it's like ground vehicles, primarily ground vehicles driving. There's aspects of exploration and aspects of wanting to do things quickly. So it's more of a one-to-one sort of like whatever projection there. So we do have other work where like the component technologies themselves. So the planning itself is very sophisticated. Even the user interface, even though it wasn't sort of optimized and nice, like user experience or optimized for the user experience necessarily. There are like many of the different component technologies are being used or being repurposed right now. So another project that we have going on is actually doing mapping in underground pipes. So facing some of the mobility issues that we have there. And certainly some of the direct challenges that we have in terms of mapping, which is like long, featureless, whatever environments, like hallways that are hospital testing facility are effectively now the dual to pipes underneath our streets. And another interesting thing is we're actually repurposing a bunch of the ideas in terms of semantic scene understanding, so like object identification, as well as then localization and mapping, actually in the context of municipal recycling facilities as well. So, you know, a lot of the many of the different core component, not everyone looked at the Subterranean challenge. And one of the things that we found, especially in talking to potential sponsors, was that it was very difficult for people to see the utility like of this work if they didn't work in the underground environment. And I guess one of the things that I really, you know, became apparent to me as time went on, and well, I think as even at the beginning of the program was apparent to us, was right that these technologies and putting them together, the underground environment in that particular deployment scenario, I think was an important part, obviously, of the SubT challenge. But for us, it was sort of a nice way to bring together a bunch of technologies that were otherwise disparate. So now starting to see the individual synergies between like planning and perception and planning and mapping and whatever, and being able to really push, not necessarily just with the core tech package from SubT, which we are, but also in several other different directions. And I'm sure Basti has numerous examples of his own as well. But yeah, so the continuation of these ideas, I guess the point I'm trying to get across is sort of is vast across our different projects, and having this competition to really force us to put this stuff together and see what works and what doesn't work, and you know what's going to be compatible with what's going to run on what computer architecture, and just figuring out all of those nuts and bolts. Is much more than like 3 years worth of normal advancement, right? I mean, it's more like a decade or a quantum leap, which I think is sort of which is the one of the objectives of these programs in general.
Yeah, cool. Yeah, this is our AMA session, or ask us anything session. So if you still have any questions, we have a couple minutes. I think one of the things that I just want to mention again is, I think it's been really awesome. It was a really good experience, and we've had a really awesome team also to work with. Lots of good people, and it was really everybody put in everything to get us where we are, and I think now is actually an interesting time. Where there's a lot of technology ready. And I think the challenge has had also some impact, beyond the beyond the challenge, with these projects, but There's even a company called Canary Aero that makes special drones for underground flying. That's kind of spun out of the team. Okay. Well, if there are no more questions, I think we can wrap up. Thanks everybody for joining, and on the 19th we'll have the seminar. If you want to go for more of the technical details, kind of one by one, and thanks for dialing in.
Thank you, everyone.